just past 10, so let's get started. So, as you can see, I hedged my bets. So the original title said 5 problems, but depending on how fast we go, there may be more, there may be less. Okay, so I've just left it at some problems. So it says school programming problems, but of course I'm not going to make a distinction between programming data structures and algorithms. So there will be problems which require one or different aspects of these. So it's not only about programming, but it's also not only about algorithms and not only about data structures. So I hope that some of these things will be new and interesting for some of you. Okay. So this is something which many of you would have seen, right? So this is a motivating problem for why you need to do things efficiently, right? So supposing you want to take a collection of numbers and validate them against another collection of numbers. So for instance, you need to check that a collection of people who have got SIM cards have given valid Aadhaar numbers. So for every SIM card, you need to check the Aadhaar number entered in that against the list of Aadhaar numbers, right? And if you do it naively, then for every SIM card, you will have to do every Aadhaar number, and that would be too slow, right? So if you do right, if you do this, then you will essentially write right. So if you do it this way, right, then how many of these are there? Huh? What is n? It's about the population of India, okay, roughly. It's not that everybody has one SIM card, but many people have 2 or more, and the number of SIM cards is roughly the population of India. Okay, how much is this? Right. So again, if you round off, right. So this naive loop takes 10 to the 18 comparisons, and 10 to the 18 comparisons under any reasonable circumstances will take you several thousand years. Right. So the motivation, therefore, is that this should be replaced by so you have a SIM card with an Aadhaar number which has been given by the person who applied for it, and you want to check it against the Aadhaar database quickly, not go through every Aadhaar card. And for this, you want to do binary search, basically. So you want, but for binary search, you need the Aadhaar database to be sorted. Okay, so my question today is, how are you going to sort it? Right? So what does an Aadhaar number look like? Twelve digits, right? So we know that there are this many Aadhaar numbers roughly in existence, but imagining that, as we always should, that this is not the situation forever, right? So it's not that necessarily the population of India is going to suddenly become huge, but people are born, people die, and presumably Aadhaar numbers are not going to get recycled for some time at least. Okay, so there will be a situation where more Aadhaar numbers are generated than are currently living people in India. Right? So Aadhaar is not that old, so we haven't reached that stage yet. But you can imagine 100 years from now, there will be a big increase in the number of Aadhaar numbers used. So in principle, how many Aadhaar numbers could be there? right? This is how many? This is 9 zeros, right? But in principle, you could have basically 1 with 12 zeros minus 1, right? That's how many Aadhaar numbers are there. So in principle, we have this many possible Aadhaar numbers, okay? So if I'm really talking about the problem in today's circumstance, I'm asking you to sort 10 to the 9 Aadhaar numbers, but I want a recipe which will work smoothly even up to 10 to the 12. Okay. So you all know, how do you sort this? How much time will it take? If I use a good sort, how much time should it take? Is quick sort a good sort? Worst case? So quick sort is not n log n in the worst case. It's a good sort, but it may or may not work on a given input. Right? So we can take, but there are other sorts. Name one, which is guaranteed to be n log n. Merge sort, for example, right? So merge sort will be n log n, but what is the difficulty with merge sort? You need to always copy the two merged lists into a new list, right? So you need order n space, right? So for example, if you use merge sort, right? So my question is there some other way to do this? I mean, so this is technically correct. Okay. The other thing you should remember is that we have to also think about how we are going to represent this Aadhaar number, right? So this Aadhaar card is 12 digits. So if we think of it as 12 digits, like the way we would actually write it, right? If you enter an Aadhaar number in a form, what do you enter? You enter 12 characters, right? So the digit is each is the representation of the digit. It's not the number, but the character 1, the character 7, character. So it's actually 12 characters, right? So in a representation, typically this is, okay, and if you're just using some simplistic thing like ASCII, it is at least 12 bytes, right? So there is an order of 10 blow up because it is 12 times whatever, right? So it's 12n is the space. If you have n Aadhaar cards, then 12n is actually the space. So if you have 10 to the 9 Aadhaar cards, your space is actually 10 to the 10. Okay? It's 10 to the 9 for the purpose of time, but when I say order n, it is actually 10 times n. Okay? So this is most of you should know how to solve this in n log n. Okay, because merge sort most of you have seen, and it's not very difficult, right? So the question here is, this is obviously not the answer I want. Right? So the question is, what else can you do? Yeah, but the problem is I have a set of Aadhaar cards. Right? It's not in my hands. So what? So how would you do? What are you asking? No, we are not giving. They have been given. Okay, so over time, so first of all, if you have ever got an Aadhaar number along with somebody else, like say a family goes to get themselves registered on Aadhaar, they will get totally different numbers. So it's not even that they are giving out in sequence or anything, right? It may be in some global sense, it might be in sequence, but certainly at a given center, you don't get it in sequence. But we are not handing out Aadhaar cards. So we are collecting. So therefore, you got, for example, you go to a voting booth and people come and they use their Aadhaar card as proof of ID. So you'll collect all those Aadhaar cards and then there'll be some random order. So that is the problem. The problem is the Aadhaar cards are already issued. Each of them is this 12-digit number and we want to sort them. And in the limit, we want to sort every possible. It's not maybe a limited thing. Our voting booth is a small sample, but all people across all service providers who have registered for SIM cards is a larger sample. But in principle, it could be anything. Right? So therefore, I'm saying, let's assume it is all Aadhaar cards. It might even be all Aadhaar cards in the future, but the format is fixed, right? 12 single digits. So we could, of course, do merge sort, right? But now notice that in merge sort, right, with 10 to the 9, what is n log n? So log 2, right, is log 2, or what is log to the base 2 of 10 to the 9? Right, this is 10, never forget this, right, 2 to the 10 is 1024, right? So what is log of 1000 times 1000? Log of 1000 is 10. Log of 1 million is 20. Right? 2 to the x times 2 to the x is 2 to the 2x. Right? So log of 10 to the 9, so if you do it in base 10, it is clearly 9. Okay, but even in base 2, it is 30, so it is of the order of 9 only, 10. Okay, so we're going to get something which is 10 to the 9 times 10, so this is going to be roughly 10 to the 10. Right, but now my problem is that it could be much larger. Like we said, it could be of the order of 10 to the 12 if every possible Aadhaar card number has actually been used. Right, and then it will be times 40, right, which would be 10 to the 13, right? So 10 to the 13 is already 1000 times 10 to the 10. So it's going to be 1000 times slower if we actually saturate our database of Aadhaar cards and use merge sort, right? So that is the situation that I want to try and avoid. Okay, so that's why I'm trying to ask whether there is a different way to do this. Okay, so it is not a standard solution that will work for every kind of sorting problem, but we have to exploit in some sense some particular features that we have in this problem in order to get something which will help us get a little bit better than this. I mean, I'm not saying that we're going to get something like which will happen in order 10 time or something, because you have to read all the Aadhaar cards, right? So you can't see. Remember that to sort all the Aadhaar cards, you have to read them. Okay, so you cannot do something which is smaller than n. So the question is, can you keep it closer to n than n log n? So in n log n only adds a factor of 10, but it could be important. The other thing is that in merge sort, if we are going to use merge sort, it will also end up using that much extra space. Right? So 10 to the 9 is 1 gigabyte. So this is going to happen, I mean, in this limit, you're going to use 1 terabyte of space extra. Right? So these are the considerations. So that's why I've asked how much time, how quickly, and how much space do we need. So I would like in some way to constrain both of them to the extent possible. I mean, we're not going to get magic, as I said. Okay? So the hint is that we are going to use something about Aadhaar cards, right? So Aadhaar cards is 12 digits. But why did we get this number 10 to the 12? Right? So we can take these 12 digits and think of it as a 12-digit number. Right? So an Aadhaar card is effectively a 12-digit number. The fact that it is written out as 12 individual digits is, of course, the way we write it out, but we don't think of it as a quantity. because it's not a quantity, but we couldn't think of it as a quantity, as a number, right? So now, what can we do? You can have. I mean, there's nothing to stop you. I don't know if Aadhaar cards are issued without zeros or not, but there is no a priori reason. Like, if you get OTPs from banks, sometimes they start with zeros. So there are 6 digits normally, but those 6 digits could be any digit. Right? So if you have leading zeros, then the number is a number smaller than, but that you would expect, right? When I say all numbers from up to 10 to the 12, I start with 0. So it doesn't really matter whether there are leading zeros or not. That is not really, doesn't change the problem in any way. You could assume that you start with 1, but it doesn't, it just reduces it by 1/10. Okay, so this is a suggestion similar to that suggestion, but slightly different interpretation. So list right, so 10 to the 12 minus 1, all 9s, right, is the largest value that you can get from another number, right, 12 9s, and 12 zeros is the smallest value. So if you think of them as integers, it is from 0 to 99999, which is 10 to the 12 minus 1, okay? 9 times 10 to the 11, whatever, that thing, okay? So his suggestion is list all the numbers and what? Right? So what does that mean? That means that in some sense you keep all the possible other numbers which are there, and when you read a number which is whatever 1 2 3 4 5 6, you go to that number and you tick it off, saying this number. So remember the other property of other numbers, there are no duplicates, only one ideally. Okay, so no two people are going to have the same other number. Okay, so how much space does this take? N how? Where are you going to keep this? Right? Yeah, so we are on the right track. So you need to do this, but you don't want to actually keep an array of numbers, right? Because that will again be the same thing. We'll have 10 to the 12 times the space to write the number, and the number is, even if you think of these as numbers, right? So even if you think of these as so an int, right? An int, if it is 32 bits, right? If I think of these as numbers, the way that numbers are represented in a programming language sense, right? So an int occupies a fixed amount of space depending on the language and what you have declared it to be, right? So if it is a 32-bit int, which used to be the standard for quite a long time, right? Let us say that we are using unsigned because we don't need to waste one bit for the sign, right? So what is the range? Right, same logic. What is 2 to the power 32? We just did it. It's 10 to the power 9, right? So this is approximately 10 to the power 9. Okay, so this may just about work for today's Aadhaar numbers, but it's not going to work for tomorrow's Aadhaar numbers. Right? So we have to go to 64 bits. Because you can't program your computer to work with 40 bits and all that. It doesn't work. Okay? So you have 64-bit numbers and you have to store 10 to the power 12 of them. So you have, what is 64 bits? 8 bytes, right? So this is 8. which is only marginally better than storing the Aadhaar number itself as 12 bytes times 10 to the 12. But this is on the right track. So what do you do instead? So do you need a counter? Are you counting? Right? We just need to know, we will never see the same Aadhaar number twice. Either we have seen it or we have not seen it. Right? So we just need to record no or yes. How many bits does that take? 1 bit, right? If it is 0, I have not seen it. If I have seen it, it becomes 1. Right? So I just need 10 to the 12 bits. And the position of the bit will be the number. Right? So I need right? So we just have a long sequence of bits. So depending now on which programming language you use, you can actually work at bit level quite easily. So you can take a bit and flip it. Right? So basically we use the position. So we just have a bit array in some sense. Okay, a bit string, which is initially all zeros, and there are as many bits as there are possible numbers that you are looking for. So I read this Aadhaar list from beginning to end, and if I see the number k, if I look at the Aadhaar number and it is the number k, I go to bit k and flip it, make it 1. So at the end of this whole sequence, I have zeros and ones in this bit string. And now I wanted to sort it. Well, I just read the bit string from left to right and I count all the ones. Right? So every 1 is an Aadhaar number which is there in my list. Every 0 is a number which is not there. So I just read off the ones, but because I'm doing it from left to right, it is automatically in increasing order. Right? So right? So when we read Aadhaar number j, we just flip bit j, and then we So how much time does this take? Right, I have to scan the list once. I can assume that this bit is like an array. I can get to the jth thing by just doing some indexing. I know where bit 0 is, I know where bit j is, and so on. So that's usually a single calculation. Just like if you go to any array and you go to the jth position, normally you can do it in a constant. So setting that bit to 1 is a constant operation for every j, but I have to do it for each, right? So I have to do 1 pass of all my Aadhaar numbers, which is n steps because there are n Aadhaar numbers. And then I have to do 1 more pass of this bit string, right, in order to extract all the ones from left to right and rewrite my Aadhaar list. So now there is a small technicality here, which is that this bit string is actually going to be, because I don't know, even in the today's 10 to the 9 Aadhaar numbers, there could be numbers which are larger than 10 to the 9, because any number which starts with a 1, for example, will have 1 and then 11 digits after that. So it's going to be something of the order of 10 to the 11 or more. So there may be lots of zeros and comparatively the number of ones could be few. So the first pass of reading the numbers is order n. The second pass of reading this thing is order of the range. Okay, so that is some slight thing. But if the worst case issue is that the number of numbers and the range are of similar magnitude, right, then it's basically 2 times n. Okay, so it's actually 2 times the range, more accurately, of numbers possible. So you avoid that log n factor, and the extra space that you need is basically, instead of the range multiplied by 8, it is the range divided by 8. Right? Because each one byte now represents 8 numbers instead of 8 bytes representing one number. Right? So this is number 1. Okay, so everybody got this? So right, so this is linear in the range, right? And the space is also, I mean, already the space was only linear in the range, but it is kind of 2 orders of magnitude. So it's like 64. So times 8 is, okay, so space is, okay. So these are small, possibly incremental things, but useful, right? So this is, as I said, the first one that I wanted to do. So this idea that, so when you look at sorting as a problem, the assumption is that the only thing you're allowed to use is compare two numbers and decide which one is bigger. So under this comparison idea of sorting, because if you don't have any information in advance about how the values are represented or things like that, you can't do anything more than compare them because you don't know exactly how they are represented. Okay? So in that model, you can't do anything better than n log n. Okay, that you can prove. But if you have information about the representation of the information, right, you can do much better. So this is one example where we have actually taken a bit sequence and done it. Okay. So now there are other ways you can do it. So right, so what you can do, so you can take my stream of n other numbers, right? And then you can right, you can do a 10-way split. You can bucket them into those which start with 0, those who start with 1, those who start with 2, and so on. And then for each of them, now you know the first digit is the same. So you have to sort 11 digits. And you can do the same thing and so on. Right? So you can do this, for example, with also things like mobile numbers. Right? You have 10-digit mobile numbers. Each digit is 0 to 9. So you can bucket them by the first digit and bucket within each bucket, subdivide the bucket and so on. So you can do these kind of tricks, but you're exploiting really the fact that all other numbers are all 12-digit numbers, all mobile numbers are 10-digit numbers, and they're all represented in that way and so on. Right? So if you can use the representation to your advantage, you can sometimes do some indirect attack on the problem and represent the values in an alternative form. So here what we are saying is that these numbers are meaningful as sequences of digits, but they are also, we can think of them as numbers and make use of that fact. Okay? Okay, so that's enough of that. So here's a slightly different type of problem. Okay. So I have a string. Okay. And now I want to say rotate it twice. So what this means is that first I put the G here, okay, and then I put right. So the problem is clear. I give you a string. This string could have some n characters, and then I give you a number k, right? So if the k is the number of times I want it to rotate. Now if k is equal to n, what happens? K equal to n, I come back to the same thing. So k could be arbitrary, but you can divide it by n and get the remainder because each n contributes nothing. Right? So if k is, for example, this has 7 characters, if I say rotate it 10 times, then you only need to rotate it 3 times because the first 7 will return it back. So in general, k will be smaller than n, but even if k is bigger than n, what you need to do is take the remainder, right? K divided by n, take the remainder, and that's your real k. So how much time does this, what I've done, take? Imagine that this string is in an array. Just, it need not be a string, it could be an array. Okay, so I have an array with n elements, and I want to take the last element and put it in the first position and shift everything by 1. That's one rotation. How much time does that take? Order of n, right? I have to move n things. Right? Everything has to shift by 1. Right? I cannot reallocate a space in the beginning of the array and move it there because it's an array. Right? So array has n slots. Those n slots have to rotate. Right? So every rotation by one step in this takes order n time. How many rotations am I doing? K. Right? Right? So this is going to take time proportional to k times n. No. So that's why don't think of it as a string. Think of it as an array of n elements. Right? So what is your suggestion? Yeah, but how long does it take to take that substring? Yeah, but how much time does that take? I mean, to write it is one line of Python code. How much time does it take to execute, I'm asking you? And where is that string? I want to rotate it in place. I don't want to create a new string. Right? So that is the hidden part of the problem. So I want to rotate this. So this is a sequence of locations, n locations, where I want to rotate within that space. Right? So imagine that you have no, one more list, same list, no extra list. Yeah. So if you can copy it to another thing, as she was saying, you can do that, right? So you can fix an index, so you know how many to skip. So you can go there and copy, and so that is of course something that you can do, right? But we don't have, I mean, you can use some extra space perhaps, but you can't use like order of n space, okay? So I don't want to have, so I should make that more clear. So I want to do it.
So instead of copying the whole list, if you only take first 8 numbers to another list and then perform the rotation with one go into the list, since it's movable, like you just change the values and then copy it down the first k numbers to last.
Tell me again.
So now, for example, if I take this, so instead of doing this, you know, like right here the k times is going to be 3.
So I have a to the okay. So this is what I have, and you want to now. So this is where I need to break it.
And then we can assign, we can perform this, we just assign a of n minus k plus 1 to in the position of a of 1. And then I can move this in the reverse order.
So you're going to exchange these two.
Yeah. And that one we can make so that it was changed.
No, but now A1 is coming after A of n minus k, right? So like if I did, for example, if no, I'm just trying to understand. So supposing I say A, B, C, D, E, F, G, and I say split it here, right? So you will get F and A, and you will get G and B. And then okay, very good. Okay, so this, so what is he saying? He's saying right, this is what we want to do in the general case, right? We want to take the last k elements and move them to the beginning. Right? So his suggestion is first we do this. How do you do this? How do you do reverse without calling a Python function called reverse? If I give you an array, how will you reverse it? Right, so you keep an index pointing to the first index. So if you have 0 to, in this case, n minus k, right? So you put some, whatever, I equal to 0 and j equal to n minus k. So you exchange ai and aj. Then you increment I, decrement j. And you keep doing this until I and j meet or cross. Okay? So that way you exchange the last pair, then you exchange the second last pair. So each of these, so it's going to take time proportional to half that length. Okay, but it's going to do it in without any extra space except, so I said you're allowed to use extra constant space. That means you can use few variables, I, j, k and all that, but those variables are not, it doesn't matter whether you're using 1 million characters or 50 characters, it's only those, the same I and the same j are going to use. Right? It doesn't depend on the length of the list. Right? So you can do this reverse in one pass of that segment. So it's going to take order n time. Or order whatever, n minus k time. The same way you can do in order k time, you can start from n minus k plus 1 to n, and again keep two pointers I equal to the same pointers you can reuse, right? N minus k plus 1. And now he says, read this whole thing backwards. Right? So that's what the first line says, right? That's what we want. Correct. So you will first do it to n minus k, k, and then to n. So you will do basically three, in worst case, if say k is half of n, right? Then it will be n by 2, and then n. So it will be order of 3n, which is order of n. The important thing is that it is independent of k, right? It doesn't matter whether I ask you to rotate it 17 times or 25 times or 2 million times or whatever. I mean, assuming it's a long enough string. It takes you only 3 of these reverse operations. Right? Yeah. But as I said right at the beginning, the constraint is that I don't think of this as an array. I don't want to allocate any extra space or move it. So I want an in-place thing, right? So imagine just always imagine physical, okay? I have, whatever, I have 1 million boxes. and I want to rotate the contents of the boxes. I cannot manufacture 75 extra boxes out of thin air. Okay, I only have those 1 million boxes. I have to work with those 1 million boxes. Right? So think of it like that. Right? So think in terms of some physical constraint. So it's not, space is not something free for you to use in such a case. Right? So you actually have maybe some, whatever, it's a factory or something, and you have some, and you want to take the contents of the last bin and put it in the first bin. But you have only, so you can hold one bin in your hand maybe. You have one bin to move things around. But that's about all you can do. Okay? So in that kind of a situation where you cannot create arbitrarily extra space, right, you have to be creative about the space that you have with you. Right? And that's where this kind of thing comes. Okay. Good. Okay. So this is another type of problem. So you have possibly heard of this 8 queens problem. So how many of you know the rules of chess? How many of you don't know the rules of chess? Anybody who here doesn't? You don't know the rules of chess? Huh? No. How many don't know? So that I don't have to waste my time. Okay. So chess has various pieces, okay, but you play it on an 8x8 grid. And one of the most powerful pieces on the chessboard is the queen. And the queen has a property that it can travel in one move as many steps as you want in either vertical direction, horizontal direction, or diagonally in either way. Right? So queens move in chess. So a queen can go as far as it can by moving diagonally or this way also. Right? So it has 4 different directions in which it can move. So in principle, if there's an opposing piece in that space, it can go and capture that piece and occupy its square. So if you're a white queen and there's a black square which has an unbroken path horizontally, vertically, or diagonally from the queen, in your move you can go and capture that queen, that piece, and replace that position with the new. So that is the way that the queen moves. So therefore the queen is said to attack all these squares. Because all these squares, if you have an opponent's piece there, that piece can be potentially captured by this queen. Right? So now in a standard chessboard, you have 8x8. Right? So if you have a queen anywhere on the chessboard, it will attack its row and column, plus 2 diagonals. So you cannot put any piece on that same row and that same column, which is not under attack. Okay? But you could start like this, for example. So if I put a queen here, okay, then it will attack this, this, and this diagonal. Right? So if I put a queen here or another piece there, it is not being attacked by this queen. Okay? But now this in particular will attack its, so it will attack some pieces which are also attacked by the red piece, right? And it will also attack some new places. So in this way, what I want to do is I want to keep putting queens, right? So I can now put maybe a yellow queen there, which is not attacked by the red queen or the blue queen. Okay? But it's easy to see that since you cannot put 2 pieces on the same column or row, right? There can be at most 1 on each row on each column. So therefore, if I have an 8x8 chessboard, I can put at most 8 queens in such a way that no 2 of them attack each other. Right? So this is a very standard puzzle, which is, can you now do this and actually put 8 queens? Right? So if you follow the logic that I have been following, right? So what you would do is you would continue like this, right? And then you would put, so this is the first 4 rows, and then you would put on the 5th row, you'd put it here, and on the 6th row, you'd put it here, like 1 and 2, right? It's not in the diagonal, okay? And the 7th row, you would put it here, okay? And then you will find that this particular row has, I mean, I have not drawn it very well, but this row has no free space left. Right? So I think I must have messed it up. So it should be, no, I know what I've done. So there is a spurious thing here. So this is wrong. But that was a line which I drew to represent that. So it should be here and then here. And now you'll find that you want to put it there. Right? And that is not available because it is attacked by the diagonal, among other things. Right? So you can't put the 8th queen if you just follow this kind of strategy by putting it in the next row but 2 places across. You can go up to a certain point, and then in particular you can put 7, you can't put the 8th. But there are arrangements where you can put 8. Okay, so that's an interesting problem in its own right, which is how to find, and there are many actually, it's not just one. Okay, there are many ways in which you can put 8 queens. And you can ask this question in general because the property is only that of a queen being able to attack rows, columns, and so on. Right? So you can ask if it is a 7 by 7 chessboard, how can you put 7 queens? If it is so does it work for any n by n chessboard with n queens? Right? It turns out the chessboard is very small, you can't do it. Like 3 by 3, you cannot do it. Right? So 3 by 3, you can check for yourself. Right? So supposing I put one here, okay, then I must put the other one. So the first 2 have to be like this, and then I'm stuck. There's no way I can find a space on the 3rd row, no matter how I put these 2. Okay, so 3 by 3, there are no solutions. But 4 by 4, already there are solutions. So 4 by 4 has a nice symmetric solution. Right, this one. What is the solution? Or maybe 4 by 4 also doesn't have a solution. Anyway, so I think 4 by 4 has a solution. But anyway, the point is not to solve it. Okay. So the point is that my question is slightly different. Okay. So it is interesting to solve this, but one of the things that you need to do to solve this, so there is no actual, as I said, there's no deterministic strategy to do it. Like, if these are the open spaces, then the next one should go here. Okay, there's no direct way to do that. So you have to use a style where you keep trying, and then when you get stuck, you come back and you retry the last move at every point. Like, for example, in that 8 by 8 thing, right? So we said that red queen was attacking the diagonal, the first column, and the first row. That means on the 2nd row, the first square is blocked by the column, and the 2nd square is blocked by the diagonal. So there are 6 possible positions I could have put that blue thing. So I tried in the first of those 6. And then I proceed and I see, maybe there is no way to put that thing there and then get a solution. Then I will go back and try it in the next square. So I will try each of those 6 things before I give up. Right? So this is this thing called backtracking. Okay? This is also in a way how you can solve puzzles like Sudoku. Right? If you are not doing any clever analysis of a Sudoku, you can just say, let me try and put a 3 here because currently this 3 does not violate any constraints. And then later on you'll figure out because you put the 3 there, something else gets messed up. So you go back and say this 3 should not be here, it should be somewhere. You know there must be a 3 in that grid. Right? So like that. So this is backtracking. So in this particular case, what you need to do is you need to find out where all you can put the next queen to do this. Right? So that is my question. Okay? So my question is, how do you check that with the current queens which are there on the chessboard, how do you check if a square is available or it's under attack? Right? whether it is in the row, column or diagonal of any of the previous queens that you have put. Right? The problem is clear. I want a way to quickly find out. So I want to check. So you can assume that you have some way, that this positions of the queens are given to you, right? So you have, say, right? So some k queens have already been placed and they are all at their respective row and column position. And of course, we know from our analysis that these must be in different rows, they must all be in different columns. Okay? So I have not, although you could assume that, but I'm not assuming that these queens have been placed row by row. Okay, so they could be that I'm trying to put on the, so first of all, it's n by n. Right? So I'm trying to put on row 99 and some queens, there are maybe 200 rows and 200 columns, and there are some queens which are in rows beyond 150 and there are some queens which are in, okay. So that's a general situation that I'm dealing with. So of course, one thing is that you know that it cannot be in any of these i's or j's. The I or the j that I am looking for matches either of I1, I2 to Ik or J1, J2 to Jk, then it's in the same row or the same column as another queen which is already on the board, so that's already out. Right? So now, for that I have to scan through all these k things. Right? So if I have already placed k queens on the board, and if I'm not assuming anything about the order in which I put them, right, then I would have to actually go through all these k entries and check whether the I or either the I matches or the j matches to check if it is in the different row and a different column. So that is the first test, is that, obviously. It should be in a different row and a different column from every other queen, but also diagonal.
I1 minus I, J1 minus J should number. The difference is same then.
Okay. So now what did you say?
The absolute value of I1 minus I and J1 minus J should not have the same number, else they are present in the diagram.
Everybody agree with this? What is this saying? So if you're on the same diagonal, if you're on a diagonal of another one, then to get on the diagonal, you have to go down one, go across one. Go down two, go across two. Go down three, go across three. So if I look at how many rows I have gone down and how many columns I've gone across, it is the same. Right? So how many rows have I gone across? It is the difference between my row and that row. I1 minus I. It could be above or below. So you take absolute value. How many columns have I gone across? It could be this way or this way. I could have gone left or I could have gone right. But again, I want to check that the new column and the old column difference is different from the new row and the old row difference. Okay. So this way I can again check with each of the existing queens, right, that this is not in the diagonal spanned by that queen. So you should check for yourself that if I put, say, right, so this now cuts out diagonals on all sides. So you have to check for yourself that in any of these positions, if I look, it will violate this. No, that is already done, right? So row column we've already done. You check that the left or the right coordinate is not the same. But now both will be different. I mean, I is not equal to I1, j is not equal to j1. But what you're checking is that the absolute difference between I and I1 and the absolute difference between j and j1 are not equal. If they are equal, then it's in one of these four directions. Okay? So convince yourself. Is everybody convinced about this? Right? So how much time does this take? Again, we have to do this for every queen. Right? Of course, we could do it at the same time as we are doing the row column check. So for every queen, we check whether I is equal to I1, whether j is equal to j1, and whether this particular difference I1 minus I, j1 minus j is equal. If any of these things turns out to be equal, then I say that this ij is attacked by that queen. If it is not attacked by that queen, I go to the second queen. I do the same thing. Check whether I is equal to I2, j is equal to j2, I minus A2 is equal to j minus j2. If it is not there, then it's not attacked by the second queen also. So already it's not attacked by the first queen. So I do this k times, and if all the k things show that none of these equalities hold, then I can be sure that none of the k queens that currently on the board are attacking this position, and this position is currently safe. That is my goal. Whether I can put a queen here or not, that's what I want to do. Okay. So in general, this. Okay. So this takes. Okay. How much space am I using? I have to remember where all the queens are, right? So again, that is order k, right? So in the limit, I will be using order n space when I put all n queens, and I'll be taking order n time. And of course, now if I take order one time for the first queen, first queen I put anyway. So for second queen, I have to look at one queen. For the third queen, I have to look at two queens. How much time does that take? Right? So if I do this for okay, without backtracking, just one, if I get lucky, right, and I find a solution by magic, okay, it'll take right. So if you have looked at all our favorite insertion sort, selection sort, this is how it works, right? The first time you insert one element, second time you have to compare it with one element and then put it, third time you have to compare it with two elements and then put it, and so on, right? So there are all of this. So this 1 plus 2 plus 3 up to n is the order n squared thing. How many of you know Gauss's proof of this? So this is a story which I mean may or may not be true, but apparently when Gauss was a middle school child, the school teacher, to keep the class engaged, asked them to count 1 plus 2 plus 3 up to 100. Right? So like our string reversal problem, Gauss did this. So it is 100 times 101, but I've added it twice. Right? So 1 to n is n into n plus 1 by 2. Okay, this is Gauss's proof. If you remember this, you'll never forget this. Okay, whether or not Gauss proved it this way, it's a good story. Anyway, so that is the point now, is that we have got this situation where we are using linear space, but we are essentially taking more and more time to analyze a position as the number of queens grows. Right? So my question is, can we do this? Yeah. Negate from where? From where? I mean, where? What? No. What are you storing that you are removing from? Index of row and column. I can agree. Right. So row column, we can imagine like we did for our first Aadhaar card thing, right? So you initially maybe you keep a bit sequence from, because it's convenient, from 0 to n minus 1. Right? So the n rows and the n columns, you can keep a bit sequence saying if it is 0, there is no queen on that row. If it is 0, there's no queen on that column. And when I put a queen at ij, I will set bit row I to 1 and column j to 1. And then this is what you're saying, right? So therefore, I can easily keep track of rows and columns that way. So now when I try to put a new queen at ij, I go and look at row I, which is already 1. Then I don't care whether it was the first queen or the kth queen. Some queen has set it to 1. I know only one queen could have set it to 1 because I cannot ever put two queens in the same row. Right? Like that Aadhaar number is never going to come twice. Right? So I can basically keep right? So when I put a queen at I comma j, I set the ith column index to be 1, and I set the ith row index to be 1, and the jth column index to be 1. And before I do that, I will first check that it was 0. Right? Okay. But what about diagonals? Hmm? Yeah, so how do I characterize these diagonals in a smarter way is the question. Hmm? That is assuming that there is a queen at the top left or in that main diagonal. That is the principal diagonal that you are referring to, but they may not be. Maybe I started off by putting the first queen in the middle of the first row, and I never actually put something on that. So maybe the diagonal is actually open. Right? There's no reason why I must start at the top left corner or put something on that diagonal at any point before the middle. Right? But you had something to say. So did people hear what he said? So let's look at that thing, right? So what did we say? So let's remove these absolute values. So let us do a concrete case. Right? So this is a queen I1, J1, right? And this is the square which I am examining. So what did we say earlier? We would say, so because I is bigger, I will write it this way. if this is the case, if the displacement in the rows is equal to the displacement in the columns, then this is on that diagonal. Agreed? This is what we checked earlier. We said absolute value, because that took care of the other three directions also. But this is a concrete case. Okay, so what he's saying, if I move things around, right, if I take the j from right to left and I take the I1 from left to right, then the difference between the row and the column at this position is the same as the difference between the row and the column at that position. Right? And you can check that anywhere on this diagonal that is an invariant. Right? So say I take the principal diagonal, 0, 0, the difference is 0, 1, 1, the difference is 0, 2, 2, the difference is 0. If I go off by 1, row 0, column 1, the difference 0 minus 1 is minus 1. Next one is 1, 2, minus 1, 2, 3, minus 1. Right? So if I do this diagonal, right, then the row minus column is an invariant. Right? So if I look at every square on that diagonal has the same row minus column value, and no two columns have the same value. Right? So if you draw it on a simpler board, so if I do this one, right, so this is 0. Row minus column is 0. What is this one? Row 0, column 1. Row minus column is, right? So this is the diagonal whose difference is minus 1. This is the diagonal whose difference is minus 2. This is the diagonal whose difference is minus 3. And finally, this diagonal, which is only one square, is the one which is minus 4. And if I go the other way, this is plus 1. So how many diagonals are there? Right? Think of it this way. There is one diagonal which starts from the corner. And then for each n minus 1 positions, a new diagonal starts that way and this way. So it's 1 plus 2 times n minus 1. Right? No, so just think of it 9, yes, but what is 9? So it's 1 plus, right? Because if I take out the one which starts at the corner, then there are n minus 1 columns to its right and n minus 1 rows to below it. And each of those positions starts off a different diagonal. So that's why I get 2 times n minus 1. So I have n minus 1 diagonal starting to the right of the top left corner, n minus 1 diagonal starting below. So that is the minus 1 to minus 4 and the plus 1 to plus 4. Because n is 5 here, right? Plus 1. Right? And if I simplify this, it is 2n minus 1, right? 2n minus 2 plus 1. So basically, if I have a standard chessboard with 8 by 8, I would have 2 into 8, 16 minus 1, 15 diagonals. But it's 2n. So it is, so remember that we are resigned to keeping linear space. Because even if we are explicitly keeping the queens I1, J1, I2, J2 and all that, right? We were keeping linear space. Now we have used linear space, whether we are particular about bits or bytes, it doesn't matter. We have used linear space to keep this column record and the row record. We said we have n rows, n columns, and we are recording for the jth row and the jth column, whether it is there or not. Right? So that is one order n, that is one order n, this is a 2n. What about the other way? Right? So if I go the other way, so earlier we were counting these diagonals. Now we are counting these diagonals. Right? So this is I1, J1, and say this is Ij. Right? So now if I want to keep things positive, I don't want that absolute value business. Right? then I is bigger, j is smaller. Right? So I want I minus I1, the difference in the rows, should be equal to J1 minus J, the difference in the columns, so that the sign is not ulta. Right? Earlier we had said absolute value. I minus I1 absolute value, J minus J1 absolute value. If they are equal, they are in the same diagonal. But I want to distinguish the two cases. So if it is both, if it is on the right, on this diagonal, then I is bigger, J is bigger. If it is on this diagonal, I is bigger, J is smaller. Right? So I'm taking the new I minus the old I, that is a positive number, and the old J minus the new J, which is a positive number. Right? So now if I rewrite this, what do I get? If I move things around. Right? So one set of diagonals is numbered as minus 2n minus 1 to plus 2n minus 1, right? Minus 4 to plus 4, based on the differences. This one is numbered from, so if you do this explicitly again, let me just create a, okay. So this is, right? So these are the row and column numbers. Right? So this one, this diagonal has R0, I mean row 0 and column 0. I is 0, J is 0. So this is diagonal number 0. Okay. This one is diagonal number. Right. So the row is, right? So it starts from 1, 0 and it goes to 0, 1, or depending how you want. So this is 1 and so on. And this is 4 plus 4, 8. Right? So it goes from, there are 9 of them. That time also we had 9 going from minus 4 to plus 4. Here we have 9 going from 0 to 8. I plus j goes from 0 to 2n minus 2. There are, in general, there are 2n minus 1 diagonals that we already argued, right? 1 plus n minus 1 plus n minus 1. So the numbering starts at 0, and you have to count n minus 2n minus 1. So it goes to 2n minus 2 is the last diagonal, right? So now we have basically rows 0 to n minus 1, columns 0 to n minus 1, diagonal, say this direction, which is minus 2n minus 1 to 2n minus 1, right? And we have diagonals in this direction, which are 0 to 2n minus 2, right? So this is order n, this is order n, this is order n, this is order n. I mean, so I basically have some 6n, right? n plus 2n plus 2n roughly. So I have some 6n things that I have to keep track of, but now I don't have to remember any queen anymore. So every time I add a queen, I first check for this ij, is row I empty, is column j empty, is I minus j empty, is I plus j empty. Right? If all 4 are empty, I make all 4 of them full. The other nice thing about this is that when I take a queen off the board, that's a little more tricky actually. Okay, so we have actually looked at the easier case. Right? So if you are taking a queen off the board, a square could be attacked, as we saw, by more than one queen. So the fact that a queen goes off the board doesn't mean that all the squares it was attacking are no longer attacked. But it is correct to say its row is not attacked by it, because no other queen can attack this row. Only this queen is on that row. No other queen can attack this column. No other queen can attack this diagonal. No other queen can attack this other diagonal. Right? So now if a new square comes, you can again check it. So adding and subtracting a queen in this representation just requires to either set all 4, first check all 4, and then set all 4 from 0 to 1. Or removing queen means take all 4 must be 1 now, because the queen is there. just reset all the ones to zeros. You have undone this queen without explicitly remembering where the queen was. The queen was implicitly at the row and the column that it is associated with. But when you want to remove the queen at ij, you just reset I, reset j, reset I minus j, reset I plus j. Okay, so this is a very clever, and this takes constant time regardless of how many queens are there. Because you just have to check 4 things and update 4 indices. Right? It doesn't matter if it's a 700th queen in an 800 by 800 chessboard. Right? It's not proportional to the number of queens you've already put. Right? Okay. Okay, so a spy reports that one of the king's wine bottles has been poisoned. And there are 10,000 bottles. Okay, so the king has a kind of manual way of fixing this. So the king has a collection of rats which can be used to detect the poison, but it takes a rat 1 hour to react and die. Okay, so obviously you have to sort of take a syringe or something and take out a little bit of wine from each bottle and inject it or give it to the rat. But if you do this 1 rat at a time, right, then it's going to take you how many hours? 10,000 hours. Right? Or you can have 10,000 rats and you can kill one of them in 1 hour. Right? So you don't want to use 10,000 hours, you don't want to use 10,000 rats. Okay? And of course, in the worst case, it could be the last bottle. Okay? Because you don't know which bottle. Yeah, no, you can use a rat twice if it doesn't die. You can use a rat once till it dies. And you're allowed to kill more than 1 rat. Okay, so it's not required that you kill only 1 rat. Yeah. Okay. Okay, so we have 5,000 and 5,000, and then 2 rats, 1 rat. Okay, 2 rats, 1 rat. I mean, I leave it to you. What are you going to use? 2 rats? Okay, so 2 rats. Right? So his suggestion is you split it into 2 equal halves and take a sample from each bottle in the first half, create a larger sample, which is a mixture. So the assumption is that even there's a trace of this poison, this rat is going to die in 1 hour. Okay? So after 1 hour, one of these 2 rats has to die, assuming that the spy is telling the truth. Okay? So then what do you do?
We go to that part, then try again.
Okay? So let's assume that it is this half. This is that dies. Okay? So then you would split this again, and again put 2 rats.
The 1 rat did not die and the other.
Okay, I can reuse the rat. Okay, 1 plus 1 rat. Because you have 1 live rat. It can get drunk, but it's still there. Okay? And so on. So how long will this take?
Log 10,000. We can use instead of 2, can use even 10.
And how many rats are you going to use? Roughly the same, right? I mean, as many times as you run the test, you have 1 plus that many rats, because each time you have to add a new rat. Good. So now can you do a little better than this?
With 10 rats,
10 rats, you can do.
10 splits. Log 10.
How are you going to do 10 splits?
We can have 10 splits and then
10 splits, 1,000 each. And then,
the same.
okay, then, but you have more rats. Then.
Yeah, I have more.
Yeah, so that you could do. You could do 3 splits, you could do 5 splits, you could do 10 splits. Agree. But I'm saying this process, can you do any better than this? So I have now so what is log 10,000? What is log 1,000? Yes. So this is roughly 10. 2 to the 3 is 8, 2 to the 4 is 16. So log of 10 to the base 2, somewhere between 3 and 4. Right? When you multiply, you add. So 1,000 times 1,000, you add 10 plus 10. 1,000 times 10, you add 10 plus 3 point something. So you can't have, unfortunately, you cannot use 13.3 rats, so you have to use 14 rats. Okay? So, okay, so you need about 14 rats, but anyway, so you have this many hours and this many rats. Okay. We already know that you can do it with 1 rat if you just do it one at a time, right? Bottle 1, bottle 2, bottle 3, and when it dies, you know that that was the bottle, right? So you could do it with 1 rat, but if you want to do it in this way and save on time, right, you need more rats, okay? And the ideal thing, you can do it in one shot with 10,000 rats, right? You can give each rat a different bottle and have 1 rat per bottle and observe which one dies, but you have 9,999 rats which you are going to have to then let loose, right? So my question is, can you now reduce the time but keep the number of rats roughly the same? I said you can reduce the time to 1 step, 1 hour, if you assemble 10,000 rats. Right? Do you agree with that? Right? So can I do, let's for the sake of argument, can I do 1 hour but with smaller number of rats than 10,000? Okay, this is where we are. Right? So what I want to ask is, can we somehow compress that thing that we were doing into a smaller time frame? Yeah, but see, the trouble with random is that we want to make sure, so even that 1 rat 10,000 hours is only a worst case thing, right? If the first bottle was poisoned, we'll do it in 1 hour. So random, the problem is how do you get a kind of estimate of the worst case time? That's what you have to. So I really want something which is guaranteed to finish in 1 hour, but which could use some number of rats. I don't want to use 10,000 rats. Okay? And it's unlikely that it will work with 1 rat. But can I work with a small number of rats? Okay. I'll give you a hint. Yeah, there's no limit to how much you mix. How? Yeah. Yeah, but 60, but then you have to check all 60, right? So 60 into roughly 16 is 9,600. So if it is not the first 60, you have to try the next 60 because it might survive. Yeah. No, I'm saying use 14 rats.
You can give a certain interval of minutes. Measure the time.
No. So, but what? You're going to send out rats at 10-minute intervals into this. But how are you going to do it? How are you going to arrange the bottle? What is the bottle distribution? I mean, what is the strategy for distributing bottles to 14 rats?
Yeah. So we are splitting, right? In the same method, we give the first half, take two rats, and give it the 0th minute, and give the next bottle to the same rats in the 10th minute or something like that, and we measure when the rat, one of those rats.
Okay, so that way you can check. Okay, if it dies after 80 minutes, you know that it was the bottle that it got at 20th minute, right? But then how many bottles are you giving it, and which bottle of that 20? I mean, are you giving it one bottle at time 0, one bottle at time 10 minutes, or are you giving it a collection of bottles? And if you're giving it a collection of bottles, then how do you then?
Interval, like 16 total bottles divided by the interval for 1 hour, we 10, right? We have 10, right? So we divide it by that interval.
But I wanted to finish in 1 hour, by the way.
I have say 5,000, 5,000. But parallelly, what I'm doing is I'm taking 2,500 of one half, 2,500 of the other half, and then putting it, feeding a third half, and then parallelly doing that 1,050, 1,050 of the halves.
No, but again, which halves, right? Because you have to try all halves. Because in the earlier case, you were waiting to make sure you knew which half was contaminated, and making sure that the next generation of rats are only sampling from that. But if you're doing this, then you're trying to guess in advance, or you have to use twice as many rats because you have to. So in the interest of time, I'll give you a clue. Can you be more? Is each rat a binary string? Yeah, so each rat is a digit, is a bit, right? So you have R0, R1, you have 14 rats, right? So now supposing I have bottle number 17, say. Right? So it has a unique binary expansion, right? So it goes right. So bottle number 17 is in binary is written like this. So I give bottle number 17 to R0, rat 0 and rat 4. Right? So I take each bottle, I take its numbering. I know that it can be numbered in 14 bits, right? Because we said that 2 to the 13 is 8,000 something and 2 to the 14 is 16,000 something. So 10,000 can be numbered in 14 bits. So every bottle has a unique binary expansion. So I take its binary expansion and I put a drop of that bottle into each rat which appears as a 1 in its binary expansion. Which rat is going to die? more than one. So the rat that gets this bottle is going to die, and that is all those rats which are in the binary expansion of this particular thing. But there is only one bottle which will kill exactly those rats, right? So for example, bottle 1 would also have gone to 0. But if R0 and R4 die, then it is not bottle 1 which is to blame. Right? So by looking at which rats die, you know the ones in the binary expansion of the bottle number. Rest are all 0 because those rats did not die. So you have the bottle number. 1 hour, 14 rats. No, I write out the binary expansion. I'm going to give, I have assembled these 14 rats and they have some 14 bowls in front of them. So I go to the rat corresponding to bit 0 and bit 4, wherever this number has a 1. So supposing I take another number like bottle, say 21. Okay, so that will be 10101. So it will overlap with these two, but it will have one extra position which is 1. So bottle 21 will go to 3 rats. Bottle 17 will go to 2 rats, which are also in bottle 21. So if bottle 21 is the poisoned one, right, then 0 and 4 will die. But because 3 also dies, I know it's not bottle 17. If it had been bottle 17, 3 would not have died. Right? So from the which rats have died, right? So unlike the earlier case, so how many rats die in that one? In every round, 1 rat dies, right? And we add a new rat. Right? So there are log many rounds, there are log many rats that die. Here, all rats could die. Or maybe only 1 rat may die. Or no rats may die. No, we start with bottle number 1. Okay? So we assume that because we have to put it somewhere. Right? So we make sure that numbering is from 1 to 10. So 1 rat may die. It could be 1 or 2 or 4. If it's a power of 2, only 1 rat will die. So a variable number of rats may die and up to all log 14 may die, but I'm not guaranteed. Earlier, everybody except the last rat died. Okay, so I'm also in some sense being rat friendly in this. I'm not killing all the rats. I'm using 14 rats, but not all 14 may die. Only as many as are required to name that bottle die. Okay, so this is so basically what are we doing here? We are basically, the first thing was a kind of a binary search, right? We were searching for this thing by dividing into half, but now you have an overlapped binary search. So we're in some sense combining those 14 stages of binary search in one stage by using the fact that the bottles are numbered. And so we can actually associate that number with the signature of the result, in this case, which rats died. So I'll skip this. Okay, so so this is another king, right? So the other king, this king has a lot of ministers, 1 million of them apparently, right? And he believes that all 1 million of them are corrupt, but he only wants to set an example with one of them. So he wants to find the most, so the index of corruption according to this king is that how much personal wealth that minister has. So he wants to take the wealthiest minister and chop off his head. Okay, so presumably the prime minister is not included in this list of 1 million corrupt ministers. So he entrusts his job to the prime minister. But the prime minister, unfortunately, doesn't have the resources to do this in the time available. Right? Because if you have to check 1 million ministers in a year and he can only investigate 3 ministers a day because that's the resource that he has available to check the wealth. Right? So in 3 ministers a day, you can do roughly 3 into 365, so roughly 10,000 in a year. So the prime minister comes up with a different strategy. He knows his king is pretty dumb, right? So he says, supposing I put all the ministers around a round table, which is how they sit in the parliament or whatever. If I can point to a minister who is more wealthy than his 2 neighbors, the king will be fooled into thinking that this is the wealthiest minister and I'll chop off that guy's head, right? So now you have reduced the problem to 1 million ministers sitting around a table and finding any minister in that 1 million who is more wealthy than the left neighbor and the right neighbor. Right? So that's the question. So you have right? And you want to find some two positions here such that so each you can assume, I mean, these are all ideal problems. So you can assume that no two ministers have exactly the same wealth, so you won't have any tie issue, right? So they will all be of different numbers. So you have 1 million numbers, if you want to think of it that way, 1 million different numbers, and you want to identify a number in this 1 million different numbers. They could be of arbitrary size. All you want is to find a number in this ring which is bigger than its two neighbors. And you want to do this within 365 days. So of course, I could do this in a sequential way, which won't work. I can look at M1, M2, M3. If that doesn't work, I look at M2, M3, M4. If that doesn't work, I look at M3, M4, M5. So that will be the same as essentially checking, because I can do 3 at a time. So remember, our Prime Minister has resources to check 3 at a time. So you can investigate 3 at a time in 1 day. Right? So that is the limit of what you can do. So you can do 3 at a time, but you can do 3, 3, 3, 3, 3. But that will take you approximately 1 million days, right? In the worst case. But can you do this choice of 3 more cleverly? So you can do 3 at a time. Remember that. Okay. Okay, so say you take 3 sectors. Okay, and then choose one. So I choose, say, this one, and this one. Right? So let me call this. Then what happens? Eliminated, why? See, because I'm not looking for the biggest or the smallest. I'm just looking for, they could not, that person who is going to be executed, unfortunately, may not be actually the wealthiest person. It just happened to be sitting next to 2 people who are neighbors who are less wealthy. Right? So I cannot, I mean, there is no, what I'm saying, there's no logic or justification to tell me which of these is not a candidate. It could be that M3 is the smallest of these, but it could be that M3 happens to have 2 neighbors which are smaller than M3, whereas neither M1 nor M2 have that. Yeah, you find the wealthiest among these 3, but I'm saying that wealthiest person may not be the one who wants. So for example, it could be that in the initial sector, they are seated in increasing order of wealth. So M1 is wealthier than these guys, but M1's left neighbor actually has more money than M1, and M1's right neighbor has less money. So clockwise, if you go, it could be increasing up to a point. But if you go increasing all the way from the lowest one, right, then when you reach the maximum guy will be bigger than the second last guy, and it will be certainly bigger than the smallest guy. So then the correct person will get executed, but only one person is there. Right? If I actually sequentially arrange the ministers in their order of their personal wealth, then the correct guy will go. But there must be one guy, at least. But there could be more than one. Okay? So minister's target is to find anyone, which the Prime Minister's target is to find anyone who is bigger than the neighbors, because that is enough to convince the king. So that there is at least one is easy to justify, because the maximum guy has to be, wherever the maximum guy is sitting, has to be bigger than his 2 neighbors. Right? So there has to be at least one. But there could be more than one, and it may be faster to find. That's the question. No, but finding the most wealthiest is a problem, right? We can only examine 3 people at a time. So it takes that many days. If I have to scan n people, it takes n by 3 days to scan all of them and collect their wealth before I can determine who's. And n by 3 is already a big number because, as I said, in 1 year you can only do about 1,000. So even if I have 10,000 by 3, 3,300, I cannot do it in 1 year. So that's the problem. And I would have to do them separately because I can't, these 3 teams cannot be done in parallel. Right? I only have 3 investigating squads which can go and raid people's houses and look under the mattress for suitcases and all that. Examining precisely what you said. I can look at M1, M2, M3 and determine. So in some sense, if you can imagine that these are all numbers which are hidden. Okay. So if I look at M1, M2, M3, in one day I can extract the numbers corresponding to M1, M2, M3. And then I have them open. Right? So you have 1 million numbers which are sealed. In any one day, I can open 3 of them. So imagine you're playing a game like memory, right? You know memory. So you have all the cards in front of you and you can open 2 of them. But then after they're open, you keep them open. Then you can open 2 more. But at every turn, you can only open 3. And you have only 365 turns.
Those lesser than them will go.
No, but lesser than that, you don't know them until you find them. You have to find them to know which lesser. It costs time to find out the values, unlike in the other kind of situation. So there is a cost involved because it has to be, as I said, in this scenario, a team has to go and raid that person's house, collect all the assets and evaluate, and that takes 1 day. And there are only 3 such teams.
Where we set a benchmark, when you assess and find the
Yeah.
value of that should be the benchmark. Those below that can be eliminated.
Yeah, but those below that, I'm saying you can't arbitrarily know how many are below, how many are, because I don't know the range of values and I don't know the values until I go and assess. So I can only 3 at a time, I can check, are they smaller than this and eliminate them, and that again is going to take so many days. So let us look at this scenario, okay? So this is not a bad way to start. So I check these 3, some random 3. Okay, they need not even be specifically at any position. They need not be equally spaced or whatever. So what can I say about these 3? Yeah. So it could be that right, it could be looking like this. M1 is smaller than M2 is smaller than M3. Right? Or it could be, so there are many possibilities. Right? I'm only interested in bigger and smaller. I don't care how much bigger, how much smaller. Okay? So it could be on the other hand that M1 and then M2 is smaller and M3 is bigger and so on. Right? But whatever happens, one of these 3, because I told you that all of them have different numbers. So one is biggest, right? And one is biggest means it's a circle, right? So M1, M2, M3 and M2, M3, M1 and M3, M1, M2, if I look in that order, there is no big difference as far as the information I get, right? So I can always put right? So I can always put the biggest guy in the middle. Right?
They need not be adjacent.
No, these are not adjacent. They are somewhere in, but we can assume without loss of generality that say M2 is the biggest. Otherwise, you can just renumber them. Okay. So essentially what we want to do is we want to keep shrinking this interval. So maybe I will just leave it as an exercise to you. Okay, but what you can do, because we are running out of time, is that you can now look at this case and you can see whether I can now probe a smaller segment in this section. Okay, and in some cases you might want to probe this section. So basically you have to decide on how to shrink this interval. So it's a kind of binary search. Okay, it's a kind of three-way binary search which does this. Okay, so just think about this. I'll send you a pointer to the solution separately if you can't find it, but just think about this problem. Okay. So basically you're trying to find this. So think of it as a tent, right? You're trying to find a tent of size 3. Now you have a tent of large size. So you want to shrink this tent until they come adjacent to each other. Okay, you can do 3 at a time. So that is the key thing. Right? So you can probe 3 things and then shrink the tent. So that's what you see. I know these values. I don't have to look at these values. I can probe 3 more values and shrink this tent. Right? So that's the idea. So where do I probe them? I probe them within this interval, and I keep doing that. Okay. So I will leave this as an exercise and proceed. Okay. So as I said, I had put some because I wasn't sure how many problems I will get to. So I will do one more, and this is interesting because it is a different application of a similar idea that we have. Right, so here is the situation here, right? So maybe I'll better give you. So you have, for example, 10 stations, 1 to 10, right? And you have 3 stations which have station masters, 5, 7, and 8. And you're allowed to move station masters left or right by 2 positions. So 5 can go up to 3, 5 can go up to 5 can go up to 3, 5 can go up to 7, 7 can go up to 5, 7 can go up to 9, 8 can go up to 6, 8 can go up to 10. Right? So left or right by that. So you're given n stations, some subset of them have station masters, and you are given some constraints saying you can move station masters by so much. The goal is to move them apart so that they are as far apart as possible. By that I mean, if you take any 2 station masters, the distance between them must be as much as possible. So formally, the minimum distance between any pair of station masters must be maximum. Right? So all station masters must be far apart from their neighbors. Right? So if you take the distance between all pairs of station masters and you take the smallest such distance, that must be as large as possible. Right? So in this example, if I can move only 2 at a time, then obviously, I mean, the obvious strategy is you move them apart, right? So you would like to take the leftmost person and move as far left as possible, and take the rightmost person, there are only 3, right? Move as far right as possible and see what you get, right? So for example, here, if you move number 5 to number 3 and number 8 to number 10 and leave 7 where it is, or move 7 to 6, it doesn't matter. The distances are 2 and 3. Right? Between the first and the second, there's a gap of 3, and the second and the third, there's a gap of 2. Or if you have moved the guy from 7 to 6, then you have a gap of 2 and a gap of 3. So for example, if you move this guy from here to here, right, then you will get 1, 2, 3, right? So though now I've got a gap of 4 between the second and the third guy, I've reduced the gap between the first pair to 1. So the minimum gap is 1, which is not good, right? So the minimum gap in this case I can achieve is 2, right? So now the problem is you're given all these things. You're told there are n stations, numbered 1 to n. You're told which of them have the station masters, and you're told how much they can move. Your goal is to find out what is the best you can do. No, only one move you're allowed. So in one move, what is the best you can do? Huh? No, 1 and 10 are not connected. So you only want in this one line, you want between pairs. So it's not a circle. Right? So this example shows that the strategy at the endpoints may be clear, that the leftmost guy goes left and the rightmost guy goes right. But the middle guy, whether you want to move, not move, move by more than 1. Okay. So in this case, without moving itself, you get a good answer. Or if you move by 1 in the correct direction, you get a good answer, but a different one. But if you move by 2 in the left direction, you get a wrong answer. Right? So not everybody has to move. And the challenge is to find out who has to move by how much. Yeah, but this is 3. It could be 7 or it could be 22. No, K is the number of positions you can. K is not your target. K is how much you're allowed to move. Right? So K is 2. And it so turns out in this example, actually you can achieve a minimum of 2, but that's only a coincidence. K is only giving you a constraint saying I cannot move more than 2 stations. Okay, so I'll give you a hint. Okay, supposing I give you a target. My goal is to make sure that they are separated by at least capital M stations. Okay. Now, as we said, there is no reason not to move the leftmost guy as far left as possible. Right? So you have some current positions. Right? So you move this guy to the left by minus K. Now your goal is to achieve a separation of M. Right? So this is where your new position of this guy is. Right? So you go. So now this is where you would like the second guy to come. Right? There are 2 possibilities. One is it can go further than that, and one is it cannot go up to that, or one is it can come up to that, or 3 possibilities. Okay? So if it can move up to that position, you move it. Right? So ideally, you move this guy here, then you try to move this guy here. Okay, but it could be that this guy can only come up to here because K is too small. It can't move. So the first guy, the separation was already something, and then you moved it by K. Right? Then this guy maybe cannot come that distance because depending on what your target M is. But wherever this guy ends up, then again you have a new target. Okay? And this new target could actually be such that, supposing I add one guy here, so this new target could actually be such that you want to move this guy right. So remember that if my target is M, I must have at least M between each adjacent person. So once I fix the first guy, I know the second guy cannot be closer than M. Once I fix the second guy, I know the third guy cannot be closer than M. Right? So although I'm not going to give you a rigorous argument, my claim is that if you do this systematically, either you will be able to move everybody so that they're M apart, or you will say M is not possible. Because at some point you did not have enough. K was not allowing you to put the next guy where you want the next guy to be. Okay? So if I fix a target, that is I want to keep the station masters at least M stations apart, you can solve it very easily. You can say yes or no. Okay? And anytime you can say yes or no, there is a hint. So what do you do now? Right? So this is a class of problems where you can do binary search on the answer. So what is the maximum that M can be? Right? They cannot be further apart than the number of stations at least. Right? Or if you want to put it another way, if there are already some L station masters in N, then N by L is because even if they're equally spaced. So you have certainly an upper bound for what M can be. And the lower bound is 0, that they're adjacent. Right? So you pick a number which is between 0 and N by L, midway. If you can achieve it, then think about it, you can achieve everything smaller. Okay? So if there is a better answer, it is bigger. So you try between M and N by L. If you can't achieve M, then the answer is smaller. You try between 0 and M, M minus 1. Right? So in this way, you keep doing a binary search on M. And for each value of M, you can quickly determine by doing one scan in linear time. So in log of say n steps, right? So you do binary search on, let us just say that in a trivial sense, M lies in this range, right? So binary search on M. Okay, and in log n steps, you find the optimum. Right? And checking each value of M takes that procedure that I said, it goes in one scan left to right. It fixes the position of the leftmost guy, then fixes the position of the second guy, then fixes the position of the third guy, and either succeeds or fails in one scan. There is no backtracking or anything. Okay, it's a trivial linear step. So it's n log n. Okay. So this is an interesting thing that is worth remembering, that sometimes when you're trying to find an optimum value, it could be that if you fix the target, you can check whether the target is achievable or not. And once you can agree on that, and therefore and the target should be normally monotonic. You can achieve something, you can achieve something smaller. And if you can't achieve something, then you can't achieve anything smaller. So once you find out whether you can achieve a given target or not, you know whether you need to look at smaller values or bigger values for your next estimate. And in log n estimates, you can find the one which splits the infeasible from the feasible, and that is your optimum. Okay. So this is so you've seen like several. So binary search is a very kind of versatile property. Okay. So it's worth getting that kind of into your problem solving repertoire, because there are many ways in which you can do binary search. Sometimes it doesn't look like binary search, but it is binary search. Okay. So I will stop with this, but I wanted to tell you a story. Okay. So you all know Dijkstra. Why do you know Dijkstra? Shortest path. Right? So Dijkstra was so actually it's very strange that shortest path algorithm is probably the only thing he ever did in algorithms, and it was more like a kind of, I would say, an accident than anything else. So he was not at all an algorithmic theorist, but more interested in programming languages and programming in general. Right? So he was very concerned about writing correct programs and writing elegant programs and using the right data structure and all that. But he was not particularly worried about, solving something in slightly more efficiently and so on. So he was also a pretty eccentric person. So he used to have if you can call it a blog, okay, in the 1960s. Right? He used to write these like a diary. Right? So his full initials are EW Dijkstra. Right? So he is originally Dutch. So he was at a place called Eindhoven, and then at some point in the 1980s he moved to the US, and he was at Texas Austin till he died. But in the 60s and 70s, when he was very much in Europe, so he used to, in those days, it was kind of a small community, and there used to be a lot of small meetings, small discussions. So he would document various interesting things, including some random stories. Okay, so this is one of the random stories. So the story says that there was a railway company, right? And this railway company had trains in which all the coaches had toilets, but toilets only at one end of the train, of the coach. Right? Not like our typical thing, but I think Vande Bharat has only one end. Right? If you take Vande Bharat, it has only toilets are only one end. Okay, so somebody who learned from Dijkstra. So, as companies are prone to do, they wanted to cut costs. So they said, surely even one end is enough, is more than enough. Why don't we just put alternate coaches which have toilets, right? So they said, we will make 50% of the coaches without toilet at all. Right? But the problem is that this was not passed on correctly to the people who put together the trains. Right? So they were not told that these trains should have a mix of coaches with toilets and no. So there were some trains which had no toilets at all. So the first fix was to mark outside which coach has a toilet, so that when they put together a train, they make sure that it has half and half. So you can imagine that this is, again, so this is more an exercise at this point in what one of Dijkstra's favorite areas, which is how do you describe your requirement as a programmer, right? So what happened here? Right? So just because you have half the coaches with toilets doesn't mean that they're equally distributed. Right? So all the coaches with toilets are in the front of the train, and the back of the train there are no toilets. Okay. So now this was fixed by telling the people who assemble coaches that make sure that they alternate. Okay. So this is of course more work because they have to be careful when they're assembling the train and all that. But even this had a problem. Why did this have a problem? See, because these had only at one end, right? So you could have a thing which had 3 coaches, and you have a toilet here and you have a toilet there. Right? So as he said, parents of small children were not amused by this because they have to run a long distance to find the toilet. So then they said you must make sure that all the toilets point in the correct direction. Okay? So now the coaches are now oriented. You can't just put them, okay, so you have to actually rotate them sometimes to make them point in the right direction and all that. But this still has a problem because this is a Vande Bharat problem also. So you are here, but you don't know which direction has a toilet. Right? So you may start walking in this direction and spend a long time finding the toilet. Right? So guess what? Right? So then inside each non-toilet coach, you have to say this is the nearest toilet, right, at each end. Okay? So now this has a further problem because you have to point. So your toilets are oriented, your non-toilets are also now oriented because they have to be pointing towards the nearest toilet. Right? So now the situation just became impossible to manage, right? Because now there was a revolt among the people who were assembling these trains because they just could not cope with this. Right? So what is the fix? Right? So somebody got this bright idea that you just take 2 coaches and put the toilet in the middle. Right? So now within that thing, of course, there's an orientation and all that. This will point to the toilet, but as far as these coaches go, you can put them in either order, it doesn't matter. Okay? So it's kind of essentially identical, even though it could be that you rotate it and the toilet is on this side, toilet is on that side, but within a unit, you are pointing to your toilet if you're not in the toilet wala train. Right? So now the problem has disappeared. Right? Because you are now working with a different unit of information, which is pairs of coaches which have one toilet. Okay? So this is the solution. So as I said, Dijkstra calls this a parable. So a parable is what? It's like Aesop's fable, right? There is a moral to the story, right? So Dijkstra says that the person who found the solution deserves to be called the world's first programmer. Okay, so this is really what programming is about. Take the information at hand and fix it so that it works. Okay? But he goes further, of course, because he's always controversial. So he says programmers love this story. Okay? Then he says managers get more and more annoyed as the story progresses. Okay? And then, of course, his favorite dig is that he said mathematicians don't see the point. Okay, so I'll stop with that. Thank you.